All right, today we're starting chapter 5, and we're going to go through 5.1 and 5.2. Personally, I think 5.1 is one of the easiest ones because it's something that you're able to do relatively easily. And contradiction, this one's going to go a little bit into, it's kind of like related to the contrapositive, but it it seems to flow a little bit easier for the way most people would think about it. So, let's get started with 5.1. So, counterexamples are one of the easiest ways to disprove something or prove something. If you want to prove something is false, you can do it through a counterexample. But you can't use a counterexample, well, you can't use an example to prove it true. Like we've talked about before, if you have maybe the natural numbers are your domain, you can't just go, okay, I tested 1, 2, and 3 and it works, so surely it works for everything afterwards. However, if natural numbers is your domain and you go, I tested 1, it worked, I tested 2, it worked, I tested 3, it didn't, so then the statement, for all natural numbers, this happens, is immediately false, so it's easy to kind of reconcile it that way. So the way I like to think about it is, for all is a very bold statement. If you say it's true for all elements of a space, this means that if one element makes the statement false, then the whole statement is false. Like I said, you say all the natural numbers, I use 237 and it doesn't work, the whole statement is false. If it's rational numbers and I pick 72 over 3, not 72 over 3, let's say 71 over 3. There's a reason very specific for that that will come up later. And it doesn't work, then that's a counterexample. So some problems have very simple counterexamples. For all x in R, x squared minus 1 all squared is greater than 0. Well, that seems like a pretty good statement. But if I just choose x equals 1, I get 1 squared minus 1 squared. I want to know, is it greater than 0? But then I get that 0 is greater than 0, which is false. Now, I could have picked negative 1, and that would have also worked. But that one's kind of easy. You can look at that and go, oh, almost like looking at where are the roots of this polynomial. Now, if it was changed, like I said, we said 1 wouldn't work, but nor would negative 1. So this becomes true if I change it to for all x in R minus negative 1 and 1, because those are the only values that make it false. Because now x squared minus 1 squared will always be greater than 0. Because the only things that would actually make it equal to 0 are 1 and negative 1, and we've removed those from the domain. So sometimes it may be kind of like in Calc 1 where we said, how do we extend this function to be continuous, where you had like the removable discontinuities. Some problems don't have easy counterexamples. Take this one. Now, if you ask me and say, okay, well, how do you know? Well, the reason I know is, well, the book gives this one. So I know what you have to pick. This is what you have to pick. Now, the thing is, if you were to get to that, it might be very similar to how we did like in the previous one where we had like the 1/2 x squared plus y squared is great, or just x squared plus y squared is greater than xy. And we had like done the factoring and everything for it. This one, I will leave it to you if you want to plug it in and see that you eventually just end up with xy is greater than xy. It's just a lot of mostly just algebra and arithmetic that you have to deal with. So let's say we have a couple examples. So for every n that's that's an integer, if 4 divides n squared minus 1, then 4 divides n minus 1. Well, let's try this. All right, if I let n be equal to 1, 4 does divide 0, and 4 divides 0. Okay, so that's true. I don't need n to be equal to 2 because that's going to give me 3. That doesn't work. But if I pick 3, so like this would be the n equal, like if I did n equals 2, I would get 4 does not divide 3. So it really doesn't matter about the second part because I've got a false, implies, whatever. But if I get to n equals 3, then I get 9 squared, or 9 squared, I get 8, third time's the charm. I get 9 minus 1, which is 8. So 4 does divide 8. But if I do this, 4 does not divide 2. So it said for all n that are in the integers, this was true. We found one case that makes it false. Now, if I were to take this function, which is kind of odd, the next one. So again, the first one is false because it said for all n this happens, and we found one n where it does not happen. So then if I pick this one, now looking at it, it's kind of hard to see what you need to pick. Because you think, okay, well, what if I pick 1? Okay, that won't really work. What if I try all this? For this one, notice that it's x squared plus x divided by x squared minus x. So I could factor out an x from the top and from the bottom, and I would get, come on, it's not that hard, x plus 1 over x squared minus 1. Which is basically the same thing as this. However, it said that it should work for any integer. This has mentioned nothing about exclusions, nothing from the domain being excluded, anything like that. So if I pick 0, and remember, I'm plugging it into the original, not the reduced. Why did I make that x squared minus 1? I just left it. There we go. Now it's right. Then what I get is 0 squared plus 0 divided by 0 squared minus 0 equals 0 plus 1. I should put a question mark over that. Over 0 minus 1. But then I get that something that's undefined is equal to negative 1. And that's not true. The thing is, even if I had picked 1, I would still get undefined equals undefined, which is true. And so any other value is going to make this a true statement. But just be aware of what you can kind of look for. Look and see, like, can you factor something out? Can you, maybe multiplying something out will give you a better idea. But so with this one, we had to look a little bit more closely for the counterexample. It wasn't as simple as just test a few cases. Now, if you just went straight to 0, because, well, I always say, if you can use 0, go for it, then it may have been the first thing you actually found out. But this is one where you have to be very careful about it. So, counterexample, like I said, we go through that relatively quick because you get the concept pretty fast. If it says for all and I find one that does not work, then it's false. Pretty straightforward. Contradiction is a little bit more, what's the best way to put it? It's a little bit more involved. And it's similar to a direct proof, except you kind of are trying to show basically some logical fallacy about it. So, as I said before, it's kind of like not necessarily the sibling of the contrapositive, but maybe a first cousin. So when we have a contradiction, we say basically the way I think of it is, why not? Let's see what happens if we assume the opposite of the statement is true. And what we're going to find is this is going to lead to some logical fallacy that shows the original statement is true. This is kind of what people who mess up the idea of the contrapositive try and do, but don't end up doing it right. Like where you read it from right to left, but instead of doing that, what we're actually doing is we're kind of changing the consequence of it. So, like this one, there is no smallest positive real number. How do you go about that? If there's no smallest positive real number, then, I mean, that makes sense, because you can pick something, somebody can pick something smaller, as long as you don't go down to 0. So let's assume that there is a smallest real number. So let's just call it, for the sake of simplicity, let's call it lowercase r. So 0 is less than r, and r is the smallest positive real number. So if you look at that at first and go, okay, makes sense. Based on my assumption, I'm assuming the opposite. Now, what if I'm going to use a half because it makes sense. So if there's no smallest positive real number, smallest, not smallest, then if I do 1/2 of r, that's still positive. So that's going to be greater than 0. But because it's half of r, it's going to be less than r. And this is still a real number, because a rational number times a real is still going to be a real number. So 1/2 r is smaller than r. But we said there was no smallest, but we said r was the smallest number. Or we said r is the smallest positive real number. So then kind of how you would close out is say, kind of like before, by contradiction, the original statement is true. So proof by contradiction involves assuming the opposite and then showing that the opposite can't happen. And then kind of like with a partition, if there's only 2 options, either it is or it isn't, and you show it can't be the isn't, or it can't be the is, then the other one has to be true. This one we said there's not a smallest positive real number. Proof by contradiction says assume the opposite. There is a smallest real number. So if we go on to another one, so no odd integer can be expressed as the sum of 3 even integers. Whoops. Assume it can be. So what we do then is we say, okay, let's take what we know. So we're going to say let x y in z, b in z2k, just as a way to represent even integers. So let's say x is equal to 2k, y is equal to 2l, and z is equal to 2j. So what I should be able to have is that there are three real numbers that are out there that are even, or three integers that are even, such that when I add them together, I'm looking at x plus y plus z equals, let's say, 2a plus 1. Right? That's what it's saying. Or that's what we're trying to show cannot happen. So if we assume it does happen, I get 2k plus 2l plus 2j is equal to 2a plus 1. Now you might kind of already be able to see the fallacy here, but we need to get it concrete and set in stone. If I subtract over 2a, I get 2k plus 2l plus 2j minus 2a is equal to 1. Now, well, let me do it this way. Instead of subtracting it over, let's just factor out the 2 from everything. So now I have 2 times some integer equals 2 times an integer plus 1. By definition, I have that an even number equals an odd number. This is false, clearly. So the original statement is, is true by contradiction. So contradiction is assume the opposite outcome. So for all a that are even and for all b that are odd, 4 does not divide a squared plus 2b squared. So take a minute and think. What's the contradiction here? 4 does not divide. Let's assume 4 does divide a squared plus 2b squared. So a is in 2k, which means a is even, so we'll just let it be 2k plus, or a is equal to 2k. B is in 2k plus 1, so we'll say b is equal to 2l plus 1. So then when I do this, I get a squared plus 2b squared is equal to 2l squared plus 2 times, or sorry, 2k squared plus 2 times 2l plus 1 squared. So through some algebra, we'd get that this is 4k squared plus 2 times 4l squared plus 4l plus 1. Distribute the 2, and I get 4k squared plus 4l squared, or not plus 4l squared, plus 8l squared plus 8l plus 2. Now, this is where we talked about beforehand making sure that you pull the correct common factor out. You could just pull out a 2, and then you would say, oh, well, this is divisible by 2. Be aware of what the question is asking. The question did not ask, is it divisible by 2? The question asked, is it divisible by 4? So this puts us in a pretty decent position. If I factor out 4 from the first 3 terms, I get k squared plus 2l squared plus 2l plus 2. Now this is good because this is not a multiple of 4, which is the same thing as saying 4 does not divide this. This number, whatever the number is. So again, the original statement is true by contradiction. So, much easier to handle. So, contradiction, I will keep saying it until it is beaten to your head. Contradiction is assume the opposite outcome. If it says this does not happen, see what happens if you assume it does happen. If it says it can't be, see if it can, and show that it can't. It's kind of like a variation on the direct proof, but instead of showing that the reason we don't say it's just a direct proof is you don't prove, it's almost more like an quote-unquote indirect proof, because you don't prove the original statement true initially, you prove that the opposite of the statement can't be true. And notice with these, they're statements. They're not they're not if-then statements. There is not a smallest positive real number. No odd integer can be expressed as the sum of 3 even integers. For every a in z2k and for every b in z2k plus 1, 4 does not divide that. They're claims. They're not if-then. If you think about it as a p implies q, you just kind of have a p. So think about when we did negations. If you negated true, you got false. If you negated false, then you got true. So if the negation is false, that means that the original has to be true. That's kind of where it comes from. And then I believe one last example. This is kind of a classic of proof mathematics. This is comparable to, I don't know, like you talk about in sports, like people would compare or this is more like, I'm not the best at sports, so let me use music. This is more like learning Bach or Beethoven. This is like the classic, or one of the classics you learn when doing proofs. Because we talk about irrational numbers and we say square root of 2 is irrational. Square root of 2 is irrational. Square root of 3 is irrational. Pi is irrational. E is irrational. And you've kind of heard that term thrown around a lot, but you may not have necessarily understood what it meant. So what we're going to do with this one is we're actually going to prove that the square root of 2 is irrational. So again, if the statement is the square root of 2 is irrational, let's try and prove that what if it is rational? So for a number to be rational, that means it has to be equal to an integer over a natural number. And their greatest common divisor has to be 1. So like 4 over 2, we would not consider rational because it has not been reduced. 3 over 2, we would, but so like 4 over 2, that would be 2 over 1, that's rational. 2 over 1 is rational. 4 over 2 is not because they have a common factor. So let's show that square root of 2 can't be represented as a ratio of 2 natural numbers. So let's just say that square root of 2 is equal to p over q. And they have a greatest common divisor of 1, because that's what it means to be rational. So if I square this, I get that the square root of 2 squared is obviously 2. And so then I get p squared over q squared. And if I solve, I get that 2q squared is equal to p squared. Now, this is pretty easy to assume, well, not assume, but state that p is a multiple of 2. That makes sense because I'm not going to be able to multiply the same number by itself and magically get something to pop out. Like, I wouldn't multiply a multiple of 3 by a multiple of 3, and suddenly it's either not a multiple of 3, something like that. You could multiply, again, 2 is not a multiple of 4, but if you do 2 times 2, you get 4. But so, let's just say that since p is a multiple of 2, let's just call p 2k. Now if I plug that in to my original equation, or I should say not original, but if I plug it into the previous one, so this is substituting back into here, then of course if you multiply it out, you get that 2q squared is equal to 4k squared, which means q squared is equal to 2k squared. Now it just sounds like I'm doing a bunch of algebra. That is technically what I'm doing, but I'm trying to get to a point. Now we have that q is a multiple of 2 as well. But remember our original statement. Our original statement made the claim that it was a rational number, which meant that p was an integer, q was a natural number, and the greatest common divisor of p and q was 1. Well, now I have that p is a multiple of 2, and that q is a multiple of 2 as well. So because of that, there's your contradiction. Because now the greatest common divisor of 2k and 2l is 2, which does not equal 1. Not the most profound statement, but it's what proves the square root of 2 is irrational. Because now I've contradicted my statement of it being rational because it's not actually met the definition of being rational. And so something as simple as not getting the greatest common divisor of p and q to be equal to 1 proves that square root of 2 is irrational. And we do that by contradiction. You assume the opposite. So if I want to prove that square root of 2 is irrational, I need to show that it can't be just rational. But you can't do a contrapositive with only one statement. So with this one, you just have to negate the statement. And then if you show that the negation is false, that means the original had to be true. Just kind of rules of your truth tables. There's one problem in the book. I believe it's proved that the square root of 6 is irrational. And you can do that in kind of like two different ways. You can kind of piggyback off the proof of the square root of 2 being irrational, or you can kind of show through a longer string of events, but ones that still work, that you still go for kind of this idea here, that the greatest common divisor comes out to be not equal to 1, And you would do that same thing for the square root of 2. So that does it for counterexamples and not contrapositives, almost said the wrong thing, counterexamples and contradictions. So we'll pick up with, I don't remember if it's just 5.3 or 5.3 and 4 in the next one.